So, good afternoon, everyone, and sorry about the slight technical hiccup. My name's Alex Finley, and I'm on the committee of the Extractive Industry Geology conferences. Welcome to today's EIG webinar, which will be given by Daniel Quinn from DustScan on innovations in dust management. Just a couple of notes before we start. All previous webinars are available on our YouTube channel, and I'll put a link into the chat box to direct you towards this. Feedback and volunteers for future webinars are always welcome. Please do not hesitate to get in contact. And again, contact details are available on our website. I'll put a link to that in our chat box as well. Today's talk will be about 30 minutes, giving plenty of time for a Q&A session afterwards. If you do have a question, please just type it into the Q&A box rather than the chat box. We'll keep an eye on them during the talk, and then I'll address them to Daniel when they're done. And with that, I'll pass over to Daniel.
Great, thank you very much. Afternoon, everyone. So my name's Daniel Quinn. I'm a senior consultant at DustScanAQ. And yeah, I'd just like to thank EIG for inviting me to give the first talk of the year. So hopefully something a little bit different, hopefully interesting for you guys as well. I'm going to be talking about some recent innovations in dust management with a particular focus on a dust prediction tool that I developed alongside my colleague Paul Eaton for use at the tarmac site at Mountsorrel Quarry. So yeah, like I said, I hope you find it interesting. So a lot of you will be familiar with this sort of foundational ideas, but I thought it would be useful just to talk about it a little bit. You know, I suppose a key way that the mineral sites and the mineral sector as a whole interact with the public is through its management of environmental issues such as dust, such as noise. When it comes to dust in particular, you know, if not managed effectively, you can have instances such as you know, the likes of a short-term dust event, so a large dust cloud escaping beyond a site boundary, that can be picked up and you can receive complaints. Additionally, these sorts of events, when left unchecked, can lead to long-term dust effects. So this example here is, you know, sort of excessive dust deposition on vegetation near a site entrance. So there's one of these things that, you know, as operators, I suppose it's important that we keep handle of, I suppose. And like I said, it can have an impact on the perception of the sector as a whole. Additionally, I suppose the public is becoming increasingly aware of these sort of the other end of the spectrum, the sort of invisible air quality end of the spectrum and how that relates to minerals working. So, you know, it's not uncommon to see news articles about PM10, about PM2.5, and now respirable crystalline silica as well as a real hot topic. So now more than ever, there's a real focus on sites, you know, to ensure that their dust levels are kept in check, I suppose one of the reasons why we started looking into this was, well, we started thinking about, well, what tools are currently available to operators, and really it boils down to, you know, monitoring is a key part of it, obviously. So we've got the sort of visible dust end of the spectrum, so the actual stuff that's landing on people's windscreens, but then we also have particulate matter monitoring, which, like I said, is becoming more of a requirement on several larger sites, especially when they are located in close proximity to residential areas. And then the other real main tool is dust suppression, you know, typically taking the form of you know, water, so tractor and bowser, road sweepers, fixed water sprays and the likes. And I suppose you can think about dust suppression as either being preventative, it can be used preventatively or it can be used reactively. So preventative being, you know, having a water bowser go around site on a schedule every day, to just keep things wetted down. Reactive might be sending the road sweeper out when there's been, you know, complaints about excess dust on a public highway, for example. So just very briefly to touch on the type of monitoring equipment that's currently really available and in use. We've got sort of disseminated dust monitoring equipment. So these measure in slightly different ways, but they're essentially measuring the same thing. So we're measuring the directional flux of dust in the air, so essentially horizontal movement. We can look at the direction of where the dust sources are coming from. And then we're also looking at the amount of dust being deposited onto surfaces. So the real benefit of these is that obviously it's collecting all dust, and it's collecting, most importantly, the visible end of the spectrum. And that's the thing that people actually complain about they can't perceive PM10. They're aware of it, but there's no perception of it. So they can't really complain about it in the same way that they would dust like this. Typically samples are left out for a week to a month, give or take, and you end up with a sort of a historic result. So the samples have to be sent away to a lab for analysis. So normally there's a bit of a lag. So normally you get the results about a week or so after the monitoring has ceased. Because of this, they're really good for sort of long-term boundary monitoring and receptor dust monitoring, especially where there's a particular focus on looking at the overall long-term trends of dust deposition in areas. And as a result, they're frequently used for sort of compliance monitoring purposes. One last benefit, I suppose, is that they can actually collect a physical sample of dust, and that allows characterization or fingerprinting of that material to take place. On the more high-tech end of the spectrum, we do have particulate matter monitoring, using these powered nephelometry-based systems. They don't measure dust deposition, they measure the concentration of particulate matter in the air. Like I said, their focus is on sort of the invisible end of the spectrum, the finer particles. Most of them can measure up to about PM20, so particles about 20 microns in diameter. So it doesn't quite, they're not quite equivalent, doesn't measure all dust. And additionally, there's no physical sample collected by these. However, the real benefit of a piece of kit like this is that it is near real time. So data is coming in live. They can be set up to send out exceedance alerts via email or text to site operators, so that if an exceedance is recorded, we can react very quickly. We can really respond to these things as quick as possible. So I suppose the two things really joining these methods together is there is a lag in response time. So best case, you're talking about a lag of a few minutes, and then it can actually about a lag of a week or two. So inevitably that means that suppression is applied after an event has already occurred, which is clearly what we want to avoid, or preventatively it has been applied as a blanket measure. However, given that, like I said, most suppression is water-based, and certainly in the summertime, a lot of sites really struggle with sort of water management. There's only so much available on a site, and clearly not all of it can go towards suppressing dust. So myself and my colleague Paul Eaton started thinking about, well, how can we add to this? Is there any other tools that we can develop to make this difficult task a bit easier, I suppose? So we started asking the question, well, what if we could predict periods of high dust risk, allowing sites and operators to respond accordingly? And that essentially means moving from a reactive approach to a targeted proactive approach. I suppose if you think about what sort of potential positive impacts you may get from something like this, hopefully we've reduced dust levels. Consequently, there would be hopefully a reduction in dust complaints. And then as a sort of a secondary benefit, we may even see, reduced water and energy usage on a site. So this was a question that we were toying with a couple of years ago, really. Essentially it boils down to, can we build some form of prediction algorithm for PM10 or other size fraction of dust? And we started thinking about, well, what data do we have access to right now that we can make use of? And the obvious one sprung to mind was, well, clearly we can look at the relationship between weather conditions, meteorological monitoring, and PM10 levels, and see if there are any factors that are sort of reasonably good predictors of PM10 concentrations on a site. That would then form the backbone of some form of prediction algorithm. In terms of how it might work then, in our idealized view, we would input forecast weather data and output a prediction based on the known relationships between, like I said, weather and PM10 conditions and other factors as well. And then that would then lead to site response in the form of targeted proactive suppression measures. A key part of it as well, I suppose, is carrying out, regular performance reviews. So assessing performance of a tool such as this against real-life monitored data to see if there are any improvements we can make to the actual algorithm, taking into account, of course, what sort of site responses have been made as well. So this was essentially what we started to do, and we specifically began work on this up at Mountsorrel Quarry, the tarmac site in Leicestershire, for various reasons, I suppose. DustScan have been working at Mountsorrel Quarry for several years now, so we're very familiar with the site. we sort of in the form of their facilities and compliance manager, Joanna Jones, has been very sort of responsive to any sort of, you know, novel approaches to dust management. Additionally, you know, we also have access to a lot of data from this site in the form of dust monitoring, PM10, and weather. And given its location in relation to the villages of Quarry and Mountsorrel, you know, there's clearly a real push from site management to make sure that dust levels in particular are kept in check. So just to give you a bit of an overview of the site, I suppose. We have the main quarry void is just here. Processing takes place here, so crushing, screening. It's linked via conveyor to the asphalt and loadout. There's some asphalt batching plants here as well. And then most of the distribution actually takes place at the railhead, which is off the screen. Like I said, the site is quite close to a number of residential areas, in particular the villages of Mountsorrel and Quarry. Additionally, in 2011, an air quality management area was actually declared for the area in green here for exceedances of PM10, the daily average PM10 concentrations. Now, levels have been reducing gradually since then for various reasons, various site improvements, but a key focus in 2021 is getting this AQMA lifted. And I suppose we have the full support of the local authorities, Charnwood Borough Council and Leicester County Council as well, because we recognise that, yeah, we're really quite close to getting levels low enough to get that AQMA lifted. So just to look at a little zoomed in area of where we actually carried out the monitoring for this project. We have a weather station and a PM10 monitor in close proximity to each other. Importantly, the monitor itself measuring PM10 is between the site and the residential areas, and it's really quite close to the nearest residential receptors. So in many ways, this can act as a bit of a proxy location or worst case scenario location for PM10 concentrations. Importantly as well, I suppose it's important to bear in mind that, you know, we've got prevailing southwesterly winds here. So the likelihood is, you know, that if we do have exceedances or dust generation on site, the monitor here will pick things up. So this is just an example of the type of equipment we used. And we started to think about, yeah, like I said, are there relationships, predictable, consistent relationships that we can see between meteorological monitoring and PM10 monitoring that we can use to build this tool? You can think of the obvious ones, such as, you know, is there a relationship between PM10 concentration and temperature? And these graphs are just from our initial investigations that we carried out back in 2018. And what we could see from this is that, you know, yes, it does look like there is a pretty consistent relationship in that as temperatures increase, PM10 concentrations also tend to increase. Now, I suppose it's important to remember that this isn't pure causality, although we do know that, you know, warmer, drier conditions increase the potential for dust generation on sites. That's just the way it is. When it comes to rainfall, for example, we see an interesting pattern. I suppose we see elevated PM10 concentrations when it's dry or nearly dry. And then after that point, when conditions are wet, we see sort of suppressed PM10 levels. Now, we don't sort of see increased suppression with increased rainfall. So once it sort of gets wet, it doesn't seem to have much of a difference after that point, which I thought was quite interesting. When it comes to wind speed, initial investigations didn't really show much up at all. We didn't see much of a pattern. There's some suggestion of lower PM10 with higher wind speeds, which seems counterintuitive. We were thinking initially potentially there was something to do with sort of greater air recharge. However, as you'll see in a couple of slides' time, when you pull this data apart a little bit more, we do actually see some pretty good relationships between wind speed and PM10. Where we did see a good relationship certainly was with wind direction. So you can see that, you know, from all directions, the average PM10, there is a certain sort of base level of PM10 concentration in the air. However, from about the southeast round to the southwest, we do see this these elevated levels. And of course, when we superimpose that onto the map of the site, it starts to make sense. We've got prevailing southwesterly winds. We have a large sort of potential source of dust and PM10 in the form of the actual site. So this is why we're seeing this pattern of PM10 concentration by direction. So we knew that there was some relationship between PM10 and weather conditions. We wanted to think about how how PM10 might relate to site activities. Now, clearly, we want this tool to be as automatic as possible. So we needed access to, quantitative data. There was no point us using sort of qualitative descriptors for site activities. And what we settled on actually was using the time of day and the day of the week as a very useful sort of proxy stand-in for site activities. So what we can see here is average PM10 concentrations per hour over a given weekday. And you see that there is sort of a baseline overnight level of PM10 that doesn't really drop much lower than this. Whereas once site starts up at around 6 a.m., we do see an increase. This elevated level stays elevated up until about 6 p.m., which is when site starts winding down, essentially. And then we do see that gradual decline in PM10 concentrations back down to the baseline. And I certainly thought it was of interest that I'm pretty sure you can actually see the lunchtime break in the data as well. When we look at Saturday's data, it'll come as no surprise that essentially a half day is worked on Saturday. So we see that same spike starting at around 6 a.m., but it gradually falls off until at around 1 p.m. Levels have reached the baseline level again. And then on Sunday, where there's no real significant work happening on site, we see consistently low PM10 concentration through the day. So we thought that was a really useful stand-in, like I said, for site activity. Another thing we did look at was seasonality, and I'll get to that in a few minutes. The important thing to remember now, I suppose, is there clearly is a relationship between PM10 concentration and just general seasonality in the data. So we've established that there is some relationship between PM10 concentrations and weather, as well as site activities. However, I think we've also established the fact that some relationships are stronger than others. That is, the ability for these factors to predict PM10 vary. So as a result, we had to calculate some weighting factors to ensure that this actual algorithm itself was as true to life as we could get it. Now, this slide may look a little bit scary. Don't worry about the numbers too much. The key thing is this is a representation of the weighting factors that we used for different variables. So the red horizontal bars just give you the relative strength of the weighting factors. It's important to note as well that the factors themselves are directly comparable between seasons here, but also between variables. So this is all on the same scale, if you know what I mean. Like I said, we broke the data down into 3 seasons, which made the most sense. So we sort of have a wet, cold season. We've got a transitional season, and then we have a warm, dry season. And then when we break the data down this way, we actually do see some pretty interesting relationships. So if we look at temperature, we've got temperature increasing as we go down the table here. We see that, for example, if we look at these really quite warm temperatures for winter and early spring have quite a large impact on PM10 concentration during winter and spring, like I said. Wherever if we look at the same temperatures during other seasons, they have far less of an impact, and the impact is felt further, essentially at higher temperatures. Same really goes for rainfall. I think, like we saw earlier, the real impact is felt when we go from dry conditions to wet conditions, and you can see that reflected quite clearly in the weighting factors. Since the initial investigations, we have actually started to incorporate the cumulative rainfall over the past 12 hours into the model itself, because we recognize that antecedent rainfall can have an impact for several hours after it's occurred. So when we look at wind speed and direction, this is when we started to see an interesting relationship between speed and PM10. During the cold, wet periods, we don't see much of a relationship at all between wind speed and PM10. And that makes sense when you consider the fact that we're dealing with wet conditions, generally speaking. Surfaces and materials are wetted down, therefore no additional wind speed is likely to sort of whip dust into the air. Whereas when we're dealing with drier periods, that clearly can have a big impact. And we do see that with increasing wind speed, we had to apply increasing weighting factors here just to reflect that increase in PM10 concentrations. And a similar pattern is seen in the wind direction, in that its impact is suppressed in wet, cold periods, and it's most strongly felt in the dry periods of the year. And then very briefly, when we look at the day and the time, which of course, like I said, is a proxy for site activity, we do see, that weekday spike again in the weighting factors, as well as we see it on Saturdays, and then on Sundays there's really not much at all occurring, which is great. So we know that these weighting factors all can be used to predict PM10. Essentially, what we then went about doing was combining these factors using the algorithm that we developed to calculate what we've called an overall prediction factor for any given block of time that we want to predict for. So then we had to go about actually taking that prediction factor and converting it into essentially a PM10 level, a risk level. And to do that, we started looking at the frequency, or essentially the probability of PM10 levels according to different prediction factors. So we've got the prediction factors running along the bottom of this graph. And then we have the frequency of what we've called low, medium, and high PM10 levels. And of course, these have been broken up according to the distribution of data that we've recorded on site itself. So the key thing is, clearly, because it's probabilistic, we do always have some chance of some overlap, as you can see here. So, the chances of low PM10 levels gradually decrease, while, mediums and highs increase. However, we do get points along the graph where essentially, there's equal probability of any of these happening. So this is where I suppose a bit of human judgment had to come into play, so that we could sort of separate all of these out and use this to predict PM10. So we settled on, in this example from the summer, we settled on sort of assigning the prediction factors low, medium, and high according to something that looks very similar to this, really. So once we've reached this point, we essentially have the sort of the back end of the tool built, and then it's a matter of actually feeding in meteorological forecast data into it. So we obtained data from an open source weather API. We got 5-day forecasts with data averaged every 3 hours, and we settled on using the 3-hourly data because that was a useful chunk of time from a data point of view to allow us to look at the trends and the relationships, but also from some sort of a site operations point of view, breaking a day up into 8 3-hour chunks was a sort of a usable amount of time. And of course, we did run some tests between, on the monitored data versus the meteorological forecast data, and we did see that there was good correspondence. So we knew that this was accurate enough and representative enough of real life conditions that we could make use of it. So to give you some examples of how the prediction actually might work, so I've just sort of invented these scenarios, really. So if we take, for example, a cold, dry, blustery weekday afternoon in winter, we combine all of these weighting factors that we discussed earlier into an overall prediction factor, and then that, based on the graph, will give us a PM10 prediction of medium. And then if we think about a warm, dry, calm weekday morning in the summertime, clearly there's a greater potential for dust generation in general. So we would expect that in the prediction, and that's what we get. So we get a high prediction here. And then finally, if we think of a mild, wet Saturday evening in autumn, so there's been no site activity for several hours, as expected, we would get a low prediction. So that's essentially how it works. And when it comes to actually using this as a tool, what we do is we generate a daily PM10 prediction that looks very similar to this. So just to talk you through it a little bit, we have the PM10 alert levels on the right-hand side of the report itself. And we've obviously color-coded these using a typical traffic light system, because of course the emphasis was always on this being, legible, quick and easy to understand, and sort of very visually impactful, and full of information, without having to delve too much into the details. Now, if the reader wants to, there are we do provide a legend that gives an actual breakdown of what each alert level means when it comes to actual PM10 concentrations. But clearly, that's not the main focus of the exercise. Given that we had an access to a high quality source of weather forecasting data, we thought it would make sense to include this in the report as well. For a couple of reasons. It means that this is sort of a one-stop shop for relevant data when it comes to dust suppression, but also then hopefully the reader of this report might start to see what sort of weather conditions may give rise to high level alert level periods. And then finally, we do also provide a summary of the next 3 days so that site can actually do some sort of medium-term planning of their dust suppression and activities, so they know what to expect over the coming days. So just because I had it to hand, I thought I'd slot this in at last minute. This is actually the prediction for today. And I mean, if it's as wet at Mountsorrel as it is here outside my window, it'll come as no surprise to you that we're predicting low levels all day today. Although we are predicting medium tomorrow, so we'll see what happens. So that's what the tool itself looks like. What sort of site responses would we expect then from using this tool? So how is it used to, you know, improve dust management? So like I said, we report this on a daily basis in anticipation of the morning site meeting. That allows staff to be made aware of upcoming periods of elevated dust risk, and then therefore they can take actions such as putting extra suppression in place in anticipation of those high risk periods. So, you know, wetting down surfaces in advance, or even potentially rescheduling certain activities known to generate dust so that they occur during lower risk periods. So we reduce the risk of any potential exceedances. So like I said, a key part of this whole process is carrying out regular performance reviews. So taking into account, you know, comparing the predictions we make against actual monitored data, taking into account what sort of site responses have been made, and then that then gets fed back into the prediction algorithm, incrementally improving it, and hopefully, yeah, we're just increasing the success rate of this predictor tool. So I'm conscious we've seen quite a few numbers and tables, so I won't dwell on this for too long. But first off, we can look at, you know, how similar the data are when it comes to the monitored versus the predicted. And if we look at the percentage of risk levels in both data sets, we see that they're broadly similar in that it's dominated by lows and there's a certain proportion of mediums and highs. We do see that the predictor itself tends to over-predict slightly. There's a couple of different reasons for that. I'll talk about that on the next slide. The main thing is it's better than under-predicting. That's the key thing. So one of the ways we really measure success is we ask the question, well, how often does a predictor under or over-predict relative to the monitored data? So if we look at the predicted low levels, for example, 86% of the time, the prediction is correct. Whereas 14% of the time, it's an under prediction. And an under prediction is when we've said it's likely to be a low, but it turns out to be a medium or a high. And clearly these are best avoided because if we under predict too much, there's a chance that we will miss the opportunity to suppress a dust event that's likely to occur. You'll note that the percentage of correct predictions does reduce as we go up into the mediums and highs. Now, there's a couple of reasons for this. One of them is that the tool itself, if we look back to this graph, because it's based upon probability, even in sort of the highest prediction factor area here, there's still a not insignificant probability of lows and mediums being recorded. So at this point here, there's a 50% chance of a high, but combined, there's a 50% chance for a medium or a low. So there's always going to be some overlap, but the tool itself was designed to be sort of conservative in nature. So it would rather output an over prediction than an under prediction if it had a chance, if it had a choice. Another reason why we may be getting over predictions, and it's something that we're currently looking at, is if it may be a consequence of site taking taking the data on board and actually responding by putting out targeted suppression. So for example, if we predict a high level and site sees this and acts accordingly, the actual event, the predicted event may never occur, and we may end up recording just a medium or a low. So this is something we're currently looking into. like I said, it's over predictions mean precautions are taken. Under predictions means there's a chance for unacceptable emissions, and we clearly want to avoid that. And yeah, sort of our mantra has always been, this has to work as a site management tool first and foremost. And it's an accurate predictor second. Although ideally we would try to get both of them going at the same time. But I think we've sort of hit the sweet spot really when it comes to balancing those two requirements. Very briefly, just touching on limitations as we finish up. Currently, this tool itself, for it to work effectively, it because it's empirical, it's based on historic data. It needs at least 12 months of monitoring to take place on site before we can really get it up and running. As a result as well, because it does look to historical data, it does struggle sometimes to predict anomalous events. So I know that a couple of years ago we had a very warm February, much drier and warmer than expected, and as a result it really didn't know what to do with itself, and it was consistently under predicting. Likewise, last year when sort of the first lockdown hit and sites were closed, it was over predicting because it expected normal conditions, and clearly we weren't in normal conditions. And then I suppose it's specifically designed to only work within a certain arc of direction, and that direction being, when the monitor is downwind of site. So this shaded in arc is essentially where the predictor works. It's not so concerned about PM10 concentrations or PM10 levels from other directions because clearly they are unlikely to be related to site activities. And we are currently working on a sort of more general predictor tool that we can use for the rest of the arc, if you know what I mean. In terms of next steps then, more sites, more data, with a view to building sort of an out-of-the-box, all-purpose tool that we can sort of immediately deploy and for it to be immediately useful on other mineral sites. And then that general tool then could be improved gradually with sort of the addition of concurrent monitoring data into that tool. We also want to start incorporating regional PM10 forecasts to get a better feel for sort of baseline PM10 loading in the atmosphere. I think we're conscious that, most of the number crunching was carried out by myself and Paul. Maybe we need to, employ some form of machine learning or something to incorporate other factors. Maybe there's other relationships that we haven't yet considered in full detail. So that's more or less it. I suppose I just want to thank, like I said, my colleague Paul, as well as Hugh Datson and Jeffrey Walton from DustScan, and then Joanna Jones, the Facility and Compliance Manager at Tarmac at Mountsorrel Quarry. And that's more or less it. So yeah, happy to take any questions.
Well, thank you very much for that, Daniel. That was really excellent talk. Apologies if I missed it, but just to start off the questions, it's what levels of dust are unacceptable for emissions?
Yeah, sure. Well, I mean, there's various different ways you can talk about that. I mean, if we're thinking about sort of, there are statutory air quality objectives, for example. So there's two for PM10. So essentially, you've got 40 micrograms per cubic meter for the annual average PM10 concentration, and then you have a daily objective of 50 micrograms per cubic meter, and essentially you're not to exceed that more than 35 times in a calendar year. But then, of course, what normally happens with sites is you will develop site-specific thresholds to ensure that, because of course, there is a relationship between sort of on-site concentrations and then sort of more regional levels. So, at Mountsorrel Quarry and at most sites, there will be sort of site-specific levels established based on historic data.
Thank you very much. And this is from Graham Green, does the prediction tool work for any material or site, or is it site and material specific?
It could absolutely work for any site. I suppose the key thing is it probably works best when we have a reasonably large site without too many other large sources of PM10 or dust in the vicinity, because clearly then we would have to spend a lot more time sort of trying to disentangle likely PM10 sources from one another. So, but yeah, absolutely, whatever. So if there's a site that has the potential to generate dust or PM10, something like this could absolutely be applied. Once we, like I said, have built a more general tool where we sort of, where the confidence in those relationships between weather conditions and PM10 concentrations and other factors are better understood on a more general scale.
And I suppose following on from that, I mean, do you have a big enough database, or have you had the time yet to think? I mean, is it a geology specific main controller, or is it climatic, would you say, at this point?
I think when we're looking at it on the scale of a site like this, in that, yeah, the focus is really on reducing levels at, like I said, a sort of a worst case location. The biggest impact is, yeah, on the scale of the site, as opposed to, and the processes on the site, as opposed to sort of more general conditions.
And I mean, have you, so sort of following on, I mean, have you looked at different quarry types and how that might affect the risk, or is it very much a site by site? Do you need the data to produce the algorithm at this point?
I think it's, at the moment, we actually know. I think the truth is we don't really know quite how much of an impact, like you said, different geological natures will have on a site. I mean, we're dealing with a big, hard rock granite quarry here, so there's a lot of crushing and screening taking place. It would probably behave quite differently if it were on a sand and gravel quarry, for example. Which is why, yeah, I suppose there was a bit of a call to arms there, saying, well, look, if we can feed more data in from a various different sites, we'll be able to, yeah, establish more general rules that will apply across the sector, as opposed to on a site-by-site basis.
Fantastic. And from Nick Horsley, do you have a view on how many sites in the UK undertake boundary monitoring, and is this carried out voluntary, or is it a requirement of planning or permitting?
That's a really good question. I mean, I don't have any solid numbers about how many sites do undertake it. I think it really comes down to the specific location of the site in relation to, clearly if we're dealing with a quarry or some sort of site, and it's a kilometre or more away from sensitive receptors, residential areas, sort of designated ecological sites, then clearly there's going to be less pressure on that site to carry out boundary monitoring. However, in the case of this and many other sites, when you do have residential areas, say within 400 meters of them, the local authorities will be aware of that and will probably push for that as a sort of a permit requirement.
And does the model equally apply to PM 2.5, or does the scope of source of the PM 2.5 provide differing results?
It absolutely could apply to PM 2.5. We've focused in on PM 10 for this one. However, and I suppose another point to add is that we're sort of using PM 10 as an indicator for all size fractions of particulate matter, as well as sort of the coarser end of the spectrum. Clearly, we can't build a similar tool for the coarser dust side of things, because, like I said, we're doing weekly sampling or monthly sampling, so we don't have the resolution in the data. But absolutely, there's no reason why we couldn't sub out the PM10 data input for PM 2.5. I think we'd probably see a very similar pattern and relationship between it and weather conditions, although clearly the concentrations would be lower.
And from Richard Small, are there any proposals for modification of site operations, fixed plant installations, mobile plant drilling and blasting, etc., arising from the use of this tool?
Yeah, so I think it's probably used on more day-to-day decision making, as opposed to longer term infrastructure changes on the site. So like I said, the key focus is, deploying suppression at the right time in the right place. Clearly, it probably goes hand in hand with sort of the more longer term improvements that sites make on an annual basis, and it may well feed into that. But I think the focus has always been on this being used as a daily tool to support site decisions at that scale, at a daily scale, or even sub-daily, really. Because yeah, I don't know if I mentioned it, but yeah, the data is broken up into 3 hourly bins. So yeah, we can sort of distinguish between sort of a morning peak and an evening lull, or whatever it may be.
And can it still be used to cover traffic dust on highways?
Quite possibly. Send me some data.
And my final question I've got up, although some more might come in,
Sure.
What techniques do you currently use to assess the composition of the dust?
Yeah, I mean, there's so many different techniques available, really. It really comes down to what the question, what questions are being asked. I mean, certainly from my perspective anyway, the things that I frequently end up doing is sticking dust under a microscope, scanning electron microscopy, ICP-MS, Raman spectroscopy even. So there's quite a lot of tools available to us. It really comes down to, yeah, like I said, what questions are being asked and what technique is appropriate. Key thing is, if we have a physical sample of material, we can throw it in most machines, zap it, and obtain some meaningful data from it.
Okay, well, thank you very much for your time, Daniel. I've certainly found that an incredibly interesting talk, and yeah, forecasting dust, great to see. But just for everyone going forward, for the Extractive Industry Conference this year, we're currently monitoring what's going on with COVID, and we hope to have a bit of news out mid to late February to update people with that. And finally, just to forecast the next EIG talk, which we've got the information in today, it's going to be in March, and it's going to be Cornish Lithium, giving an update on what they're doing for everyone. So that should be incredibly interesting. And please keep an eye out for adverts for that. On that, Clive, if you've anything to add?
Just a final point. If you've enjoyed this presentation from Daniel, fantastic, Daniel, excellent. You can go to our YouTube channel, and you will find, if you want to watch this again, Daniel's video will be up there, along with 5 other webinars from stretch back to about June last year. So we're actually building up quite a nice library of webinars for EIG. So I just reiterate, if you want to have a go yourself, let us know. Get in touch with myself or Alex, and you'll find yourself hopefully on the screen in the not too distant future. Okay, cheers everyone. Thank you very much.
Thank you very much.
Take care.